So hello everyone, and today we will be seeing one of the problem from Geeks for Geeks. It says find the peak element in a 2D matrix. Now what does it mean? Given a 2D matrix mat, identify any peak element within the matrix, but what the peak element is. The element is considered as peak if it is greater than or equal to its four immediate neighbors, which is top, bottom, left and right. For corners and edge elements, any missing neighbors are treated as having value of negative infinity. So if 10 has its missing neighbor, two of the neighbors are missing, which is up and which is left, so those are treated as infinity. And there is also a note here: a peak element is not necessarily the global maximum. It only needs to satisfy the condition relative to its adjacent elements. So that means the multiple elements can exist, and if it exists, return any one of them. Also there is a note again, note that the driver code will print true and not. Okay, cool. So we are interested in creating an array list, not returning true or false. Sure. So now we know what the peak element is. A peak element like this 30 is an element whose four sides, top, down, left and right, these are smaller than itself. So it has up, down, left and right smaller than itself, which is good, and that's the reason we can go ahead and return 1,1 because the index of this is 1,1, which is done over here. Also 2,2 can also be returned because it has valid so it's because it's a valid peak. Same goes with another matrix as well. Cool. There's one catch over here about expected complexity. You wanted to do this within n log m time complexity. So that's a good trick. If that was not a case, hey, I could just went ahead and I could just have iteration from I is equal to 0, j is equal to 0, 1 by 1, and checking up, down, left and right and understanding, hey, if it is the case, just return it. It might work for you, but again, the time complexity for such algorithm would go ahead in n into m, that is rows into columns, which we don't want, which we obviously don't want. So what can we do? What can we do here? So before jumping into code, let's understand how to approach this code. It's a very good thing to visualize the problem first and then jump into the solution, whatever it asks you. So I'll just copy the test case right now, but I want you to visualize what peak means. So what does a peak mean to you? So this is a question you need to ask yourself, that what does a peak mean to you? Peak means don't need to be a global maxima. A local maxima could also work, but the peak means to you is it should have up, down, left and right smaller than current, or in our case lesser than or equal to current where we are standing. And that's fair enough, that is so appropriate. How can we deal with this? So one thing which comes into our mind, and one thing which we can visualize in a way that understand this problem as a hilly range, that you are standing in a range where you have few mountains with you, and you are over here, a person, and there are further mountains next to you. And at this position you wanted to know that, hey, where is the peak element? You can just go ahead and check whether right hand side is a peak or a left hand side is a peak. And once you find it, yeah, you can go ahead and iterate to that. It's a very simple. You see left and right, and check out where the peak can be. And if you get peak, just walk to that direction. Cool. Nothing rocket science as such, but just an intuition, just an understanding, or just a visualization what we can make. Okay, we understood left and right, but how can we identify this position? Well, you don't need to identify this. You can just take any mid column or any mid element could work. Makes sense. You know that already. I am having a column from left to the last column, which is M, and I can take any point over here, and for the sake of simplicity I'm taking the mid, and within mid I wanted to check whether, hey, I'm at a correct position with respect to heights, because maybe that where I'm standing, the lower row or the upper row can be greater. So imagine this point, like you're standing at a position, you have north, you have west, you have north, south, west and east, and you are at this point, my friend, and you wanted to know that, hey, where I could get a peak. So you check at north, you check at south, and then you identify that, hey, north can give me peak, and then you go ahead and start walking to north till the point you are at correct row. I'm denoting row because north and south, these are traversal within a vertical space. You go I++ in the way, or you climb up the row or climb down the row. So that is why row is the appropriate term here. Once you fix the row, you check west or east, that is left or right. As simple as that. Still, if you're confused, let me clear your confusion, and most of things would be cleared automatically once we get into the code. Cool. So let's start. We will have an array list, which would be our return. Rest is equal to new array list. This would be our result, which would be returning this point. And as I mentioned, we would have left and right, where L is equal to 0 and right is equal to a dot length minus 1. And since we are dealing with columns, I just don't want a of 0. And while left and right are correctly within the limits, I wanted to go ahead and work upon them. How do I work upon them? I take a mid, L plus R minus L divided by 2. Once I get the mid, I'll get the appropriate row. Get max row, I'll say. Get max row for A with mid as element. This max row is nothing but a function which would do a very simple thing, which would give us an idea that, hey, this row for that column is the maximum. So this is a column, and I'm saying that int row is equal to 0 for int I is equal to 1, I is less than a dot length I plus plus. And if at any point of time I'm finding that, hey, a of I and column is greater than a of row and column, then row is equal to I. So you see, we are focusing only on the maximum elements, and that's what we want. We are focusing on maximum element, means a greater positions, means we are going towards peak. So return row. Once we get a maximum row, we are at a correct position. Where do we want it to be? Just check it over once. Before checking, just understand who are your left and rights. So L is equal to, I'll say left because L is already occupied. So left is equal to A of row because we are on the appropriate row, and mid minus 1. Obviously, this can only be possible if mid minus 1 is greater than or equal to 0, but in case if it is less than 0, in that case I wanted to consider integer dot min value. Cool. I'm considering min value if it is invalid. Same goes for right as well. mid plus 1 is greater than or equal to a of 0 dot length, and if that is the case, I'll just consider integer dot min value, else I'll consider row of mid plus 1. Cool. I'll just take max, which would be mat.max of left and right. This will give me a maximum value, and if this maximum value out of them is smaller than or equal to our current element, what is the current element we are standing at, which is nothing but row and the mid. If that is the case, result would be containing two numbers, which is row and column, which is mid, and we return the result, because as soon as we get any of the value, we can just return the result. That's not the case. But in case this condition fails, then what? Then we know that, hey, our a dot row and mid, either one is smaller than the left. Like if left is greater, read it like this: if left is greater than our current element, I wanted to shift my attention towards left, so right is equal to mid plus 1. Sorry, left right, so right is equal to mid minus 1, because I'm more focusing on the left. I'm updating my right to left to shrink and focus upon left. So left is equal to mid plus 1. In case it's going wrong, focus on right, and I'll here say focus on left. And ultimately, this condition, if everything goes well, this condition is never occurring, so never should occur until and unless the requirements change and you don't want less than or equal to, you don't want strictly less than. But that's not a case. Requirements are not changing now. So let's compile this code to understand whether we are having compile safe code. So note syntax error. Let's try to submit this one, and yeah, it seems our code has been submitted and it works fine for rest of all the test cases. This was a classic and very good example of binary search. Overall, the time complexity, we are respecting the time complexity which is mentioned over here, O of n log m, where m is the column and n is the row. We iterate all the rows over this function, that why n multiplied by the binary search or the left or right divide and conquer strategy we choose over column. That's why log m, and no such auxiliary space. That's why O of 1. So this was a good example of a binary search. For more such binary search content, click the video on your right, and I'll see you in the next one.